Well, it gives me tremendous pleasure to welcome back to the podcast two of our favourite returning guests, Kris Boulton and Lee Wheeler, for another of our deep dives into the wonderful world of Atomisation. Kris Boulton, how are you, mate?
Doing really well. Thank you, Craig. Great to be back.
Good, thank you. And Lee, everything good with you?
I'm good, Craig. How are you?
I'm good. We're firing on all cylinders. Now, we're very lucky, listeners, to have Kris and Lee. They're just back from their sellout UK tour of all the festivals they've been doing. So you've been doing Festival of Education, Research Ed, just chatting to Lee off mic. I think you've got Research Ed National coming up as well. Kris, what's going on here with this tour? What are you chatting about here?
Mainly it's about Lee's experiences. So I get to step back and he does a lot of the hard work. I think one of the nice things about doing the same thing a few times is because I've never co-delivered something like this before. So we've got to play around with the format and see what works best. I think we probably did our best one yet at Festival of Education. So that's all we're going to be replicating in about a week's time for Research Ed National.
Good. All right. So if you're lucky enough to catch them there, I hope you enjoy it. Right. So we're gonna just dive straight in here. This is a continuation. So if you're jumping into the series cold, you'll want to go back and listen to the first two episodes we've done, and also the big kind of intro episode that Kris and I did about a year or so ago now. We're going to pick up on a couple of things here. Some of the kind of questions we left unanswered last time. And also, Kris has had some correspondence via Substack from a keen reader, and we're going to address some of her questions as well. But before we get into all that, and we're recording this towards the end of the summer holidays, results have just come out. So, Lee, how did GCSEs go? Tell us kind of how they compare to last year, where you're happy, where the areas of development are, and so on.
I think it's quite a typical education thing to say that we're never happy. No, we were the results were going in a good direction. We when we step back and we look at the results, we're very happy. But we were looking for the stars. We were looking for 20-30% increases, and you have to sort of believe that. You have to be involved in that when you're doing it. But when you step back afterwards and you say, look, we have made great progress in a year, and we've made significant increases in our 9 to 4, 9 to 5, 9 to 7 across from last year to this year. So we are very happy with the results once we stepped back a little bit. But then, you look through the individual lists and there's just a couple of people, and you get those emotional things tying in, and that's the first response you have. And then we took a step, as I said, took a step back, and we were very happy with the results when we took a step back. The 9 to 4s increased, 9 to 5 increased. Me and James's class had the best progress throughout the year, and actually going back into year 10 as well. But it increased by a significant margin into year 11, which was nice to see. And we've had quite a lot of issues, like disruptions, staff turnover, like legacy issues that we've been trying to get rid of. And they're just going to lessen year on year from now. So we're even more positive looking into the next year.
Sounds good, mate. It's one of those times of the year, right, that every teacher, well, certainly obviously if you teach Key Stage 4 and 5 can relate to. It's potentially a sleepless night the night before, and then you often see the results before the kids see them, so you know which kids are going to have the best days of their lives and which kids are going to be a little bit gutted and so on. It's an emotional roller coaster. But it's great to see things are moving in the right direction. I think you spoke about on the first episode where your departments come from, and it's it's kind of a long way to where you want to be, but it sounds like things are moving in the right direction, and hopefully the work that you're doing alongside Kris you'll start to see that come to fruition as those younger year groups make their way forward.
This next year is the one we're really, really, really excited about. The first year, we've seen the results, and we've seen the results from sort of quite, I'm not going to say haphazard, I'm thinking of a better word for that. Like it's been the initial, the initial implementation of something is always a little bit messy, and this year is just going to be so much cleaner, and the results from that, I can't imagine how amazing they're going to be.
Tell you what, if this was some kind of documentary, we'd then cut forward 12 months' time, your head's in your hands in tears or something. But yeah, fingers crossed it's gone well. All right, that's great stuff, Lee. Right. So last time, one thing we touched upon, but I know this is a big question I certainly get, and I know Kris has had it as well, is about the role atomization can play in supporting students to get better, for want of a better phrase, at problem solving, or what is kind of often called the AO3 questions in GCSE. So for international listeners, GCSE questions, so GCSEs is the exam the kids take at age 16, and the questions are categorized into 3 assessment objectives. AO1 tends to be your kind of factual recall or real basic procedures. AO2 is when sometimes you have to, maybe it's a little bit of context knocking around or something like that. It ramps up a little bit. And then your AO3, kind of all bets are off. It could be weaving in 2 or 3 different areas of mathematics. And as many years ago, when I interviewed some examiners, those AO3 questions, one of the remits is they have to be unpredictable. They can't be things that kids have seen time and time again, because one of the tests of a good GCSE exam, or one of the criteria, is that kids should be able to deal with things that they haven't seen before and problem solve. Now, we've talked a lot about how atomization can be incredibly powerful for helping kids, for example, understand what a trapezium is and what a trapezium isn't, and how you can expand a single bracket and take it really, really far. But what about when you get one of those questions where there's 2 or 3 sentences, there's some mad diagram that no one's ever seen before, there's lines flying in everywhere, and the kids are like, what the hell's this? So how does atomization help students deal with those kind of multi-step, contextual, unpredictable questions? I'll start with you, Kris, and then Lee, feel free to come in at any stage.
This is one of those questions where, Lee, I'm going to pitch it to you pretty much off the bat. And it's because when we touched on this towards the end last time, I feel pretty confident here, but also you feel really confident about it as well. But it's something we've never talked about before. So I'm really interested in what your thoughts are on this as a serving, practicing classroom teacher, where we haven't looked at it from the theoretical angle or the principled angle yet. And then I can try and offer my version and how I try to structure it as well. Is that okay with you, Lee?
Yeah, of course. So intuitively, when I looked at it, I've thought that the way it's done, it just inherently makes it easier to tackle those AO3 questions. As you said, the main thing with those AO3 questions is you look at a combination of topics. Now, when you're learning those processes as isolated processes lesson by lesson, and you practice those processes as a full process the whole time, that's the only exposure you have to it. You don't have the capacity to chop and change those little processes you're doing. So maybe you take, one transformation from this process you did over here, and then one transformation from a process you did over here, and so on and so on. And they use that to build this sort of ultimate AO3 question. Whereas, so if you've practiced in isolation each of those individual transformations anyway, that isn't weird to you that they could slot together in a different way. It's because every single one of those has been taught to you in this one sort of linear process every single time. That's the only exposure you've had to it. That when you take in those and chopping and changing them, it becomes difficult and it's not something they're used to. The sort of structure of atomization being each of those tiny little bits being taught individually anyway means that slotting those little bits together isn't a new skill to them. It's something they're fairly used to and they become quite quick at. Is my experience initially.
Kris, anything to add there before I come back at this?
Yeah. Okay, so quite a few different things. And I think, Lee, you've honed in on one of the things that I would certainly talk about. First, let's address what that examiner said about how they have to be unpredictable. That is a nonsense. They're not unpredictable, but they're less predictable than others. Let's say that. So why do I say it's a nonsense? Why do I come on quite so strong about that? Because all of the exam boards have a requirement set by Ofqual for there to be a certain amount of reliability in the exams, which means if you sit the exam 2024, 2025, you get as close to, ideally, perfect reliability would be you get the exact same mark, certainly the same grade. Now, perfect reliability is almost impossible, but one of the ways you ramp it up, one of the ways you could get it, have exactly the same questions year on year. Now, we can't do that for really obvious reasons. So that's why you get a lot of the same questions cropping up with slight changes. Use Pythagoras' theorem to find this side in a triangle, but the triangle's changed a bit. Okay, so that's a highly predictable question that'll come up. With the AO3 style questions, sure, the exact combination might not have been there historically, but they all seem to fall into one of a very narrow range of buckets compared with what you're dealing with in the real world. So if we're talking about real mathematical thinking, goodness, the search space there is much, much broader. So it is still quite narrow. It is predictable. It is relatively trainable, I think. So for the things I would pick out, the first one is what Lee's already said. A big thing they will do is combine multiple bits of the substantive curriculum into a single question. And I think the case in point for this has got to be 2015 Edexcel exam, Hannah's Sweets. Everybody, I love reading that question because for about 7 lines, it sounds like a perfectly normal probability tree question. And then you just get to the sort of bracket A, the actual task, and suddenly it's like you've been gaslit the whole way through. And it's like, okay, so now show that this quadratic equation is true. You say, what? Um, so no wonder everybody flipped out at that, because they've every single time they've ever done a probability tree question in an exam or in school, you've always used basic numbers and you've calculated fractions for probabilities and so on and so forth. So to Lee's point, if you're well immersed in the way of teaching around atomization, when you were picking out those atoms and maybe even combining some into chains, you probably would have stuck in some algebraic expressions there. It would have come quite naturally. In fact, increasingly, I quite enjoy that because it's way easier to process the arithmetic of algebraic expressions than it is fractions. And so instead of having to deal with numbers quite often for practice or calculators, quite quick sums with very small values, usually very small coefficients. So that immediately ticks off loads of these issues right away. But there are a few other things that get thrown in there. And probably the best way to think about this, if you look at the template that I share with people, which is on the Substack, for a routine atomization. So you're going through a cognitive routine, and essentially in one column, you're just putting the output each time and then what type of atom this thing is. For most of the questions you get on the exam and for most things we teach in maths, what you get is a linear train of thought from top to bottom. Do this and then do this and then do this and then do this. That's what makes it routine. Do this and then do this. The previous atom, its output, serves as the prompt for what to do next every time. If you run the same analysis with an AO3 question, and sometimes these are fairly like best buy questions. Good example. Here are 3 different things. Which one's the best buy? Which one's cheapest? But there are others. And you don't get the same top to bottom thinking. And weirdly, you get more of these on a foundation tier exam than you do on a higher tier. So you can use the same template, you can run the same analysis. When I do this, what I find is I have to work out a number, and then suddenly I've got nothing more to do with that number. Now what I need to do is go back to the question, and I need to start a new chain of logic to work out another number. So when I do this, I stop there and I shade the next band in gray, and then the next band in white, and the next band in gray. So it gives me a sense of, okay, this is what's really happening. They're having to stop. And you imagine as a kid, you're thinking this is, well, what do I do next? And for a lot of kids, either it's just obvious. For us, it's obvious. So for some kids, it's become obvious, or it isn't, and they're just a bit overwhelmed and I don't know what to do. Like, I've got this number, but what do I do with it? And the answer is nothing for quite a while. Because what you've got to do is work out another number, then work out another number. Back to Lee's point with a best buy question, it might be that this one's asking you to process fractions. The next one is asking you to do something with compound interest, maybe. The next one's asking for something a bit more prosaic. You have to work out the 3 numbers. Then you have to bring the 3 numbers that you worked out back together and do something new with them, which in this case is a comparison. But still, nearly every single one of the questions falls into a narrow range of categories. For example, you get a lot of max-min problems. What's the maximum number that you can have for this? Okay, well, how much will that cost? A simple conversion at the end. Or what's the minimum you need in order to have a fence all around this weird geometric shaped field? Or the other one is like, do they have enough? So they tell you how much they have. Do they have enough? How much do they need? Very often they fall into those categories. Then they're bringing in different topics, like Lee said. So I think those are 2 of the biggest things to think through to help solve the AO3 problem. One is when you're teaching through atomization, you are naturally going to you're going to start combining different topics. It's really fun to do that, and it's really fun to see how successful the kids are, and they can generalize across parts of mathematics much more quickly, much more effectively. And then the second is appreciating that there is this break in the chain of logic in some of these AO3 questions. And so one solution to that could be the goal-free problems, the goal-free effect that Swallow talks about. When I've tried this with kids, I found it works up to a point, but they still eventually are a bit like, I don't know what more information I can find out. So an addition or an alternative is just to treat each of those shaded blocks almost like I'm not going to call them molecules. I'm not going to I'm not going to extend the metaphor too much, but kind of like super atoms. There's all these blocks where I can teach you to work out that one block and get you 100% of that. I could teach you to work out the other, get you 100% of that. Now I can just, instead of an exam question, instead of pulling from the exam where it might ask you to do 4 of these discrete blocks, I'm going to design a question so you just have to do 2. And I'm not just going to design a question, I'm going to design 20 questions. So you have to work out a thing, work out another thing, and then compare them, maybe. And that's hard to do. So maybe I'm going to get ChatGPT to help me design 20 questions pretty quickly. And then we could build it up from there. Okay, you've got to work out one thing, then another, then use the thing from earlier, and now compare them. So I think one of the big things it certainly helped me with is atomization, is realizing that that's what's going on, that's what these questions are asking for. It's not real world thinking. It's not genuine problem solving. It's nothing close. It is just breaking the chain of logic a little bit. And we don't really structure the practice of that traditionally in such a way that they can get comfortable with it.
Okay, lots to take in here. So I've got 4 kind of comments / reflections that I'll just go through one at a time, and then I'll just throw it out there just in case Kris or Lee has anything that they want to say. So first, to fully agree with Kris on this, I think the expansion sequence that we've talked about in the last episode and the one before, and for listeners who are just kind of tuning in here, this is the thing at the end. It typically happens at the end of a transformation, where you can really push students' understanding and knowledge of a procedure, and that is a real opportunity to weave in and combine some topics that wouldn't traditionally be combined. So if you're doing expanding a bracket, you might whiz in a fraction, you might whiz in a decimal, you might whiz in some crazy algebraic expression, and so on and so forth. So I think I agree with you there that the expansion sequence can be a real good way to set students up for this combination that can happen in exams. But a couple of other things. So Colin Foster, I'm a big fan of, and I know Colin is he wrote a reply to one of our conversations about atomization. So I've spoken to him a couple of times about problem solving on this podcast, and he talks about this idea of teaching students what he calls problem solving tactics, and he distinguishes this from when Polius starts talking about kind of problem solving strategies, like, solve a simpler problem and draw a picture and all this kind of stuff, which are so vague. I just don't think they're effective at all. So what Colin talks about is actually explicitly teaching students problem solving tactics. And often these work in geometry, like things like extend a line is often a good tactic if you've got some kind of angles problem where you don't seem to have all the information. Or if it's a circles problem, find a radius is quite a good tactic to try and whether it's working out, again, using a bit of trigonometry or finding an isosceles triangle or something like this. And there's a list of these tactics that you can explicitly teach to students so that when they see a problem where they're like scratching their heads thinking, okay, I've never seen anything like that before, one of these tactics may unlock the secret to it. So I just wanted to flag that up. I'll recap all these in a second. Third thing is, I think the biggest issue students have when it comes to AO3 questions isn't actually the Hannah's Sweets question where it's combining things in a way that they haven't seen before. It's often, and maybe this is more true of students who sit the foundation paper than the high paper, but it's those big wordy questions, Kris. It's the one where there's so much to decipher about what's going on. And this is the irony of this, right? You'll get, and it'll often be like question 17 on a foundation paper, and it's some big chatty story, and somebody's bought something, and there's a ratio in there, there's a percentage in there, maybe there's a fraction in there, there's some money in there. And the kids are like, what the hell's going on here? I don't even know where to start. And the frustrating thing there is when you go through it with them, they're like, oh yeah, if I'd have known you had to do that, it's easy, because it's the procedure's not the problem. The transformation isn't the problem. It's deciphering what they need to do from all this text. So I'm very interested to get your take on how atomization can help with those worded problems in terms of deciding what they actually need to do. And then the final point I'll make, then I'll recap this and then shut up, is I had a maths teacher called Craig Latimer on the show, God, maybe 2 years ago now, and he had a really interesting strategy for attacking these wordy AO3 questions, which I've used, and it's probably the most effective thing I've done for this, and it's certainly better than the goal-free problems that I was obsessed with for a few years, but I could never make work as well as in theory it's supposed to. So he calls them no-number questions, and it's really nice, this, because let's imagine you've got this worded question where it's about money, ratio, percentage fractions, and so on. What a lot of kids do, well, what some kids do when faced with that is they just down tools and think, I don't have a bloody clue what's going on here, and leave it out. What other kids do is they just grab the first two numbers they see and just do a random operation with it and just kind of cross the fingers and hope for the best. And then, obviously it all goes wrong from there. So what Craig suggests doing, and as I say, I can only speak for my kind of small scale experiments with this, is that actually when you give students these, but you remove all the numbers, you literally black out all the numbers, and you say to students, what's the first step you need to do to solve this problem? And what's quite nice about that is it takes away the potential distracting elements of those numbers and also removes kind of the need to do any kind of calculations. And it forces kids to engage with the structure of the problem. So they see, for example, that the first thing I need to do is work out how many students there are by multiplying the number of minibuses by the amount of students per minibus. They don't have to do 7 times 23 or something like that and then get their working memory filled with that and then just, cognitive overload and they don't know where to go. So they essentially set out a structure to solve the problem, and then when the numbers are revealed, then all their attention can be on doing the transformations or the calculations to solve it. Now, that has been my kind of way of dealing with these wordy contextual problems, and as I say, I've had relative success with that, but I just want to get your take. So just to recap on my 4 points there, first thing is I'm completely agreeing expansion sequence really helps with kids combining topics together and will probably help solve the problem with questions like Hannah's Sweets. Second, I was interested in your take on Colin Foster's idea of explicitly teaching problem-solving tactics to kids. Third, do you agree with me that it's actually the contextual problems that cause a great deal of the problems kids have in exams? And fourth, what do you think of this idea of no-number questions as a potential solution to this? There's a lot to go through there. I'll throw to you, Kris, and you can throw to Lee at any stage or whatever, however you want to do this.
Yeah, well, I mean, I was just about to drop him in it because I was speaking last, but he's taking his headset off, so I'll go for it. Taking his head. Okay, so the expansion sequences, obviously we're in agreement with that. The problem-solving tactics, Colin Foster's point. So it's interesting. I've still got a draft Substack post ready to go in response to the article that Colin wrote that you mentioned, because he misunderstood what atomization is, or at least the way that I talk about it. And so technically Bruno came up with the term, but he came up with the term to describe what I was doing. So since I came up with this as an idea based on Engelman's thing, I think I have a right to say this is the true atomization. And I can see where he's taking it from, and he talks about atomization. He contrasts it with with small steps, which I know has been popularized by some curricula out there, and they've referred to it as atomization. But these are different things. It's not about breaking down processes into small steps and teaching small steps. So I think he misunderstood a lot. And what I read in that article, I wasn't convinced at all was going to work with most children either. With that being said, I'm sure, I'm delighted to hear, and I'm sure he'd be delighted to hear that basically what you said about the problem-solving tactics, I think I agree with, based on what you've said, completely. So I didn't speak to this just to try to simplify things, but I hinted at it a bit. There's real-world problem solving, there's real mathematical problem solving, and then there is AO3 problems, which are not real mathematical problem solving. So when I talk about this with teachers, I ask them in advance to do about 15 different problems before we meet. And then when we meet, and I ask them to think about what it was like to solve the problem. And one of the things I do when we meet is I map them on a continuum from most novel to least novel. So my most novel problem is an isosceles triangle split by from one vertex to the opposing side into 2 further isosceles triangles, and then you're asked to find all of the angles. So very unusual angle chasing. Well, there's no angle chasing. It's a very unusual angle problem. No numbers involved. And the reason it's the most novel problem I know is because there's no way I can vary that problem in order to give you another go at trying something like it. It's a unique problem. It's a unique shape. But it uses strategies like labeling unknowns as X or whatever and forming equations and solving them that could be applied elsewhere. So the deep structure is obviously applicable elsewhere. Um, and then when we come to the least novel problems, every single one of them is a past exam paper question. Because they're just things where you vary the shape, change what bit of maths comes in, change the numbers, change the worded context. This is why I say they're predictable. They're not particularly novel. So when it comes to these more novel problems, the range of things you have to essentially be trained to do does expand by an enormous amount. My friends who are proper degree trained mathematicians, which I'm not, they think about problem solving in a way I don't, and they just crunch through things so quickly because they have been given a lot of these things. They do automatically think, draw in a radius, extend the line. Most of us would probably do that, but they do other things as well, which are very, very clever. So I agree with that. If you're trying to get kids to think like real mathematicians and you want them to be able to super generalize everything that they know to really, really novel problems. If you want them to compete in a mathematics Olympiad, I absolutely agree. If you want them to do well on AO3 problems on a maths exam, it's probably a bit overkill. Or at least you can do those things, things like drawing in lines, splitting a triangle into two triangles, find a right angle, that kind of thing. They're there, but there's a really finite, narrow list of them that you will ever need. And there's a limit to how far the exams will ever stray beyond that because of that requirement for reliability. So now your final two, the word problems and the solution to the word problems or potential solution, I think that's a distinct pair to the Collins idea about problem solving tactics. So before I continue, now that Lee's headset's working again, I thought I'd give him a chance to speak and we can break up whose voice we're hearing.
I was just that one part. I'm going to say it's like small. I think a lot of the problem solving tactics that you alluded that you gave as examples, I think aren't most of them transformations that would just have been taught, like identify radius. In a lot of things, I would explicitly teach that to extend the lines. I would probably teach a question where extending the lines would have been useful, and my first transformation would just be extend the lines. My first transformation when I was planning for finding the internal angles of a polygon was to cut the shape into triangles. This is something they would have been exposed to. They would have seen a lot of these tactics before, and that intuition to just do that anyway would probably be built without sort of seeing it as these tactics. It would just be an intuition. It'd be something that's inbuilt into what they would do naturally, which is kind of more what you want, really, more authentic.
Yeah,
Sorry, Kris, just on that. Yeah, I like that, and I like again, just in case I wasn't clear, the reason I'm a fan of these and why I like Colin's idea is I like anything that's explicitly taught, right, not left up to chance, and
yes,
I like the fact that this is okay. There are a set, and I agree with Kris, a relatively finite number, a relatively small number of these tactics that will probably get kids through GCSE, and you can explicitly teach these to kids, perhaps via a transformation, as Lee's alluded to there, or some other way, and we do, or whatever it may be. But I like that distinction between those problem-solving tactics versus Polya's problem-solving strategies, which I just don't find useful at all, because they're just like, well, solve a simpler problem. Well, 1 + 1 = 2 is a simpler problem, and it's not going to help me do the Hannah Sweets, right? So,
all in agreement. I think all in agreement on.
Yeah, that's it.
I was working with two teachers on this just 2 days ago on Wednesday. And one of them referenced that book and pointed out how, one of the strategies it gives you is be more ingenious.
Honestly.
Just be smarter.
Be clever.
So the thing that Lee said, we talk a lot about atomization and unstoppable learning, but it's really nice, I think, sometimes to bring it all the way back to the foundational theory, which is, of course, Siegfried Engelmann's. And what Lee was talking about set them a problem where you have to draw a radius or extend a line, and that will help you solve it. One of the principles of instruction, the core principles, or two of them really, are around sameness and difference. The idea is you're teaching what is the same in each context and what is different. And from that, you are learning to generalize. So sometimes, I think quite often we teach one thing, we teach a thing and we think we've taught it and that's it. And we don't realize the need for structured repetition So that generalization takes place. So it's not just one problem, it's and then another, and then another, and then another, where the same tactic helps you every time, but the surface context is as varied as I can make it. So you're learning that what is the same about each of these, even though they're being maximally varied, if you will. And so we're now extending the initial ideas around MPPBN into something much deeper. But then you need to juxtapose that with, oh, here's one where the surface features are the same, and yet, oh, extending the line didn't work this time. Oh, I had to draw a radius. So now you need to learn to discriminate, which is, again, Engelmann's language, juxtaposition and discrimination are his language, between those two contexts. What is different about them that means this is a radius problem rather than an extend the line problem? So I don't know whether Colin also structures the experience for students that carefully, but if he didn't, that I think would be a level up. So nothing I would disagree with there, and it would level up that way. And if he's already doing that, it's probably about as good as it can get.
Yeah, and just to give a shout out here, so my idea of these SSDD problems that I first wrote about in How Wish I Taught Maths is a similar thing here, where you've got 4 problems that look on the surface to be quite similar, but actually their deep structures are different, and it's because those surfaces are so similar, that's why you start asking the question, okay, well, why did I have to find a radius for this, whereas for this question I had to draw a line and so on. So yeah, that's why I'm a fan of those.
Okay, so your next 2 were the word problems and solving them. So
Yes.
definitely agree that, yeah, that experience as kids reading, what do I do? Where do I start? So it could be a literacy problem, but let's put that to one side because we're not very good at teaching literacy in maths classes. The second, it could be what I described earlier when I talked about the sort of breaking the chains of logic. It's not a straightforward, here's a prompt. I know what to do in response to that. I start here and I run through it. Yeah, there is this confusion of sometimes even where do I start? I have found goal-free stuff helps people get 1 or 2. It helps them start, but then they just get stuck because it's not a consistent chain of logic. So I definitely agree that deciphering the big chatty story is a massive problem. And yeah, if you start showing them what to do, it's like, oh, well, I know how to do that. Agree with the problem. Absolutely, massively agree. So how do we solve it? The no number problems, as you've described them, are really interesting to me. It's not something I've tried personally, but part of the reason it's interesting is it's very, very close to something else I'm increasingly leaning into, which is not asking kids to crunch numbers, not asking them to process arithmetic. So that's everything from the example we've had before, just tell me what would find the area of this trapezium. So construct the expression that would find the area of this trapezium, which has the combined delight of being able to make side lengths as complicated looking as you like with surds and algebraic terms and so forth, whilst being way easier for kids because they're not having to crunch the arithmetic. The arithmetic is the slow, boring, tedious, annoying thing, which we frequently ask them to do all the time. It really slows down the time we have practicing the bits that matter. Obviously, want them to be really rock solid in their mental arithmetic, but so long as they're getting enough practice to assure that, and enough contextual practice, so they are being asked to work out some areas of trapezia all the way through to the actual area, that's okay. That's enough. They don't have to do it every single time. So there's something similar going on here, and the more and more I've been doing that, the more I've realized it does. Or part of the argument I've been making for it is it does get you thinking much more about the structure of the problem. So what do I need to do? What do I need to find? Why do I need to do this? Rather than, yeah, sort of, it's almost this hang up I feel from primary school where maths was simple enough that it was mostly arithmetic and the answer was always a number. And I just need to, it's usually one step and it's usually 2 numbers. And I just need to do something with these 2 numbers in such a way that I get the right answer and teacher gives me a tick. So yeah, I can see there being potentially a huge amount of value in that as a means of liberating children from the tyranny of numbers. Do I believe in that? I don't know. I've just made that up. Maybe I'll go back on that next time.
It's a powerful insight that, though, and it's worth just doubling down on this idea that removing the need to crunch numbers is a good idea, right? Because it never happens. I watch, well, up until this year, I watched maybe 100 lessons a month over the last 3 years. Every one of those lessons, the end goal was always crunch a load of numbers and see what they get. Now, there's a number of issues. A few of these you've alluded to, but I just want to chuck an extra one in the mix there. So there's the efficiency problem. It means kids can get through far fewer problems than they would do if you didn't have to crunch the numbers. There's the, whether it's the, you call it the attention or working memory issue, that where's their attention? Is it on what they're actually doing, or is it on crunching these numbers? So all of a sudden they forget where these numbers came from and what they're actually, their end goal is, and so on. You get the issue that I wrote a Substack post about a year or so ago now, and it was all kicking off, about a girl who I sat next to during a lesson on adding fractions, and she couldn't follow the process for adding fractions because she didn't know her times tables and she didn't know her factors and so on. So, but that was what she was being asked to do. So she was putting all her attention into thinking, what's the 7 times table look like? What's 7 times 4? So by the time she got to the end of that problem, she couldn't remember the process for adding fractions because all her attention's been there. But also the extra benefit of not asking the kids to crunch numbers all the time is just from a checking for understanding point of view for the teacher, because it makes the diagnosis so much harder. If a kid gets a wrong answer, there's 2 potential reasons why they've got that wrong answer. They've either crunched the numbers wrong, or it's gone wrong earlier on in the process where they've either used the wrong numbers and so on. And when the kids are holding up 30 mini whiteboards with a load of different answers, it makes that very difficult in the moment to diagnose. So the more as teachers we can remove that final step, it just makes that, the kind of ability for us to check for understanding so much easier. Lee, I don't know if you want to come in on that. I saw you scribbling away now.
Yeah, I just had a couple of things I didn't want to forget. One of the big lessons I've had this year is to stop varying problems by changing the arithmetic. This is one of the biggest things. Like I keep pinching myself every time, and I'm getting used to it now. Like my natural reaction, my intuition is normally to come away from that now. But at the beginning of the year, I found myself doing it like every single time I wanted to go into an expansion. I was like, 476, and I'm like, no, there's no need. There's lots of different ways you could do it. Then another part of that is I found in some strange ways when I've taught algebraic fractions that a lot of my lower set kids have actually taken to learning algebraic fractions, or at least the basics of algebraic fractions, quicker than they do numeric fractions. And you think algebraic fractions you would generally class as sort of grade 5, 6, 7 topic. And you're looking at fractions as a grade 2, grade 3 topic, and they pick it up so much easier because it's all conceptual. And as you said, it's not the working memory being taken up. I've had this experience with 8A4 this year. It's just one of the things we talk about in our conferences. That I've been doing. I taught them how to expand a triple bracket, and I had them 1 lesson a week for 6 weeks, and we got to expanding a triple bracket just from sort of building that process, and they didn't have any issue. There was very little arithmetic, and I just thought that was quite a notable part, quite an important part, that there was very, very little arithmetic, and it allowed them to access something really, really quite high level. And then the only other thing I wanted to say was, for me, most of the time when I introduce a routine, the last atom, or at least the last part of it, is to teach them how to decipher a worded question around it. So, for example, I've taught them how to solve use trigonometry for soccer term. And my last one is, here's a worded question here, there's a ladder against the wall. And their first atom and their transformation that I would teach individually would be to say, ladder against the wall, this, tell me theta, tell me O, tell me H, and tell me A, if you can. But yeah. And yeah, so that's the way I kind of approach that. So they get that, for me, most of the time, if it's appropriate to a routine that I've just taught, the last part of it will be them deciphering a worded question around that. So they get so much practice deciphering worded questions that they're just so used to seeing those words be turned into intuitable numbers and values and equations. They get used to that. They practice that individually.
Just before I hand back to Kris, for me, the cherry on the cake, just to revisit what I said earlier, would be, after doing that, then to give them a set of the SSDD problems, so that then they've got to also then decipher when something that looks like the ladder leaning against the wall actually doesn't require SOHCAHTOA, but it requires Pythagoras, or it requires the angle properties or something like that. Yeah, love that, Lee. Kris, anything to add before we move on from AO3 and problem solving?
No, I think a couple of the things you've said actually are going to lead in nicely to a couple of the other questions you had for us. So yeah, let's move into it.
Teaser, love that. You can see he's a professional, Kris. Love that. Okay, perfect. Right. So, Kris has had some comments. You put a question out, didn't you? Something like, "Has anybody got any questions based on your kind of Substack post and the conversations we've had?" And Kris sent me through a reply that you've had from Jordan. So, big shout out to Jordan here. So, I've copied two of her questions that I thought I really want to know the answer to these myself. So, let's tackle the first one. If an atom is prerequisite, so to a new routine that you're teaching, and students are not secure on it, do you treat it as if it's new? So let's just put this into context. Let's go to our favorite, whether it's let's do adding fractions, everyone's favorite. Let's imagine you've atomized the routine of adding fractions, and as part of that atomization, you've realized that finding the lowest common multiple is one of the atoms that kids need to be secure on. But great news, kids did that last year, so that's brilliant. But you don't assume that just because they did it last year, they can do it now. Instead, you check for understanding, might be mini whiteboards, diagnostic questions, however it may be. And lo and behold, the data comes back that actually kids don't have a clue how to do lowest common multiple, or a decent proportion of them, whatever you set that to be. I don't know how to do it. The question, well, Jordan's question seems to be there. What do you do in that case? Do you treat that as if that atom was brand new to kids? So actually finding the lowest common multiple, you start from scratch, or do you do something different because kids have experienced it before? That was my interpretation of the question. I'll fire it over to you, Kris.
Okay. It shows like there's three dimensions we can look along here. So to simplify it a bit, to begin with, let's imagine you're a one-to-one tutor, so you don't have 30 kids in a class. And the second, I'm going to change the concrete example. I thought about fractions and LCM earlier. I think an even cleaner one is, when we come back to fractions, is you want to teach them to solve quadratics, but they can't factorize. They should be able to.
Okay.
They've learned how to factorize quadratics, but no, they can't. So you've got one child in front of you, you're trying to teach them how to solve quadratics, they need to factorize, they can't factorize, what do? You have a limited time and you're working on the fly. So the reason I like the quadratics example is because there are options obviously available to you here, where you can still teach them to solve quadratics, but they don't have to factorize. Namely, you can give it to them in factorized form and just teach them what to do at that point. You are eventually going to need to come back to the factorizing problem, but you've got a way out for the time being. You can do that with fractions as well. You could give them the LCM. You can do things to break down or to atomize how much they need to do. Essentially, we're practicing individual atoms here or subchains that get around the blocker. So in the moment, we don't have to deal with it. But okay, so we've done that, and now we've got our one kid in front of us, and they still can't factorize or they still can't find the LCM. What do we do? Is this situation different from had they never been taught it before? Depends. Could be, might not be. So if we think now about the Bjork's idea of storage strength, that's really where the question is. How much storage strength for the memory of how is there for the memory of how to factorize or find the LCM? If you've got a kid with really high storage strength, then for that memory, then it might be that you just sort of remind them. Do you remember doing this? We go through this. Oh yeah. I remember that. Oh, so hey, try this one. Oh yeah, I do it like that. Wait, would I do it like this? Yeah, you do it like that. Okay, great. Try another one. Yeah, I've got it. Are you going to go through the whole thing like it's brand new with that kid? No, because you didn't need to. In a minute or less, you're done. They've remembered what to do. What a waste it would be to start from scratch. If you tried, they'd probably interrupt you anyway and just say, "Oh, miss, sir, I get it." Or there might be that they do remember it. There is some storage strength, but it's much less. So they need much more reminder until they get there. Or it can even be the case, which is very often the case for kids in school, unfortunately. There's practically no memory storage strength there whatsoever. So in that case, I mean, yeah, just treat it like they've never seen it before, start from scratch. So that's a simple sort of continuum when you've got one kid in front of you and you can immediately diagnose what they're doing. What do you do when it's a class of 30? And the reality is you've got one kid at that top end who remembers it already, another one who remembers it really quickly, someone in the middle who will eventually remember it, and someone at the end who is, I swear, like, I'm in year 11 and no one's ever taught me how to find the area of a triangle. I swear, miss. So I mean, it's kind of dealer's choice. It's sort of up to you. What would I do? Well, again, you've got two choices even here. One is what I would probably do if I know they have seen it before, test it, see how they do, try to remind them, realize some have got it, some haven't. Be prepared to go through it again as if it's brand new with the entire class. And now it's a culture question. Can I get those who already know how to do this? Can I pitch this to them in such a way that they accept there are other kids in the class who've completely forgotten? Maybe it's their own fault because they're the naughty kids or whatever. So they're a little bit chagrined by that. I don't know. Again, we're talking about a culture issue now. Um, and therefore, we're getting increasingly into the expertise of the teacher and on the ground decision making. But yeah, one option is to try and teach it quickly. If you can see that like totally blanking, it's like, right, it's need to stop. I need to go through this in this way so that every single one of us is on board. Those of you who are already at the top end, this is where this is leading. And I'm going to make sure we include something in an expansion sequence here that is going to be delightful for you to think about and work about as well. So that's what I'm going to try to do in the most complex scenario. And then final thought on that. So we just summarize that 'cause that's probably the main lot. So you've got kids. So one, you can just circumvent the blocker for a while. Two, you can see if just reminders, showing them, going through a quick worked example, brings them all back on board. Three, on the assumption it doesn't, which it won't for, probably won't for all of them, yeah, you're probably going to have to go through the whole thing from scratch. Maybe it goes faster than it would have done last year. Maybe they weren't taught this way last year. So the whole thing is still new and exciting, even for the top end. That was often my experience when I did this stuff. You could even avoid, you can make a different decision to the one I mentioned, even rather than trying to go through it quickly with them as a reminder. You can just go in assuming they've all forgotten everything. I think 8 times out of 10, that's probably a reasonable assumption. Save some time, get through it quickly, go on to the bit you really want them to think about. The final, so that'll tackle most of these things, I think. The final thing on my mind, which is almost in this third dimension I was thinking about, we could have chosen something like negative numbers as a prerequisite. And we could have, it's an example I've talked about before. We could have talked about negative numbers as a prerequisite for subtracting equations, or a prerequisite for completing the square. About kids who can learn to complete the square dead easy, can never solve an equation correctly because they can't handle the negative arithmetic. Infuriating. In that moment, you can avoid it completely by just giving them positives and just dealing with it that way. And it's not just a small atom. Negative arithmetic is a whole unit. It's a massive amount of work to get that right. So in the moment, if I'm dealing with a class who still can't handle negative arithmetic, I'm probably going to completely avoid negative arithmetic. What is the point? They're not going to get it. They're not going to get the right final answer. But I'm going to have to do something to teach every single one of them fluent negative arithmetic. The same way we're going to have to do something to teach every single one of them to fluently handle that prerequisite atom at some point. You can't avoid it. They all need to know it. It's the nature of mathematics. So at some point, it's going to have to be taught.
Love it. Lee, I'll hand to you. I have a few thoughts on this, but I'll just hand to you first.
I've got quite a few. Yeah, I was scribbling away again, as always. So, I mean, my response, if they were taught it last year, is it is new. Even for me, I don't know, it might be different in different school contexts, but for me, even the very, very best kids, if they were taught something a year ago, they are not going to revisit it. And if they can remember it, it's because of principles that they understand around mathematics. It's not because they understand and they actually remember that process that they've been taught. So they can definitely do with being explicitly reminded of the process as it would, like that. So for me, yeah, if it were taught last year, if I weren't doing atomization, I weren't spacing practice properly with a strand curriculum, then, and I was sort of taking over from that, then yeah, I think I would just pretty much just essentially assume everything is new to every kid. That's what I've done pretty much this year. It's a bit of a reset. It's a bit of a hard job. It's a bit of a long bit of work, but if you're going to build a proper foundation of knowledge, I think it's essential. I have also found that building a culture in my class around space practice and making sure they understand the value of space practice. My clever kids, I think I'm just not really used to, at least, this kind of idea you're saying about there's clever kids getting really annoyed that we're not doing. I just have not had that experience at all, and I don't know exactly why that is. Obviously, I've got no control group to compare it to. But for me, I assume it's to do with the culture I've built around that idea that, no practice is bad practice. If it's easy, that's good. That's not a problem. Don't worry about that. and they just get on with it, and they understand that it's for the good of them, it's for the good of the class, and everyone's going in the right direction. So there's a big thing around culture, I think, in that case. And I think if people haven't sort of fostered that culture, that can be a problem, that people can get a bit annoyed. I'm not sure. I don't work in the type of schools I imagine where the kids like that are going to be. Then the other thing is efficiency. For me, the process of atomization, I'm spending 7 to 8 minutes on an atom. I can very, very, very efficiently diagnose a problem. So we come across a problem that they can't do that I think they should be able to do with the LCM, for example. I get them to list multiples. I get them to do 3 questions on that in 3 minutes, and I go, okay, you could do multiples. And then I give them a list of common multiples, and I treat it each as transformations. It's so quick to diagnose exactly what the issue was. That for me is a godsend. That's massive. That saves me so much time. And then the last one, the other thing I had just a thought of, if I were spacing properly, and I think this is quite important, and I was using a strand curriculum like I have been, and they have forgotten, and the class, like a fair proportion of people in the class, I've got it at this next space repetition window. This is when they should still be able to remember, and some of them still can't. I think it is really important then to do what Kris was saying and push them a little bit, give them some hints, give them some memory joggers, because them being able to pull that memory for themselves, if I do give it to them fresh, it will spoil the entire space process, and we will have to start from the beginning again if I give it to them fresh. So if you have spaced properly, there should be some struggle, and you should try to really push them to remember it. It is really important that they do remember it for themselves if you've spaced it properly and you're at one of those windows. Otherwise, you're going to throw away all your hard work for the most part. But if you haven't, then yeah, please just treat it as new, because it basically is new if it was a year ago the last time they did it, unless you have some genius kids that are doing, practicing and revisiting everything strategically for themselves at home, which I doubt.
Love it. Right. I've got 3 things to say to kind of, reflections on what you've both said there. 2 of which are pretty safe, and then 1 of which I'm going to push you both for an answer which can't be, it depends. Okay, so just as a little flag there. So the first is, I think something that we've not made explicit, but based on a lot of the lessons I see, I think we really need to. The fact that teachers are identifying prerequisite knowledge is something that we shouldn't take for granted, right? I watch a lot of lessons where teachers just rock up and teach something new and just aren't even aware that it's built upon something that kids have done before. So the process of identifying, which I think Kris and I have spoken perhaps in our first conversation about atomization, I think that's one of the hardest bits, is the actual breaking something down into atoms, that we actually identifying, okay, this new routine, what are the smallest meaningful bits of knowledge that kids need to be able to access it, and then which bits have they met before, which I need to check for understanding of, and then which bits are new, which I need to teach. So identifying the atoms, I think, which prerequisite I think is underrated, and obviously it's a necessary step. And then the other thing I see is, even when teachers have identified them, they don't check for understanding of these prerequisite atoms, because they just assume kids know them. As I say, they did them last year, they were great at them. They did them last week, they did them last lesson, they were great at them. But of course, lots can happen in 24 hours and 12 months and blah, 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 blah. So just checking for that understanding is a massive step forward to success. And Kris often speaks about kind of, getting 80% of the way there. If your atomization consists of listing the atoms, checking the ones that kids have met before, and teaching the ones that are new to kids, you're going to get a hell of a lot of the benefit of the things we're talking about. But here's the bit I wanted to push you both on, because this is the question I get asked the most, by far and away the most, when I talk about prerequisite knowledge, is teachers say, okay, this is all well and good. I know assessing prerequisite knowledge is really important, but when do I know that enough kids have got it that I can move on and teach the new idea that's based upon this prerequisite knowledge? So let me give you, and again, you can't say depends and you can't say culture. I want some definite, your kind of ballpark figure for this.
Craig,
so
I think you do.
You are?
There is no ballpark figure. I think you know the number. We've talked
no,
about this before.
but this is interesting, because this is different from what we spoke about before, right? Because what we spoke about before was you're teaching something new. You're teaching one of your new atoms, right? what percentage do you expect to be getting this right, and that you're happy then to move on to the next question, the next? And you both, I was like 80%, you're like, no, 100%, 100%, 100%. But we're talking about something different here. We're talking about the kids have been taught something in the past. You are checking for understanding whether that's secure or not, because you're going to build upon it on this new idea. This new idea builds upon it. You check for understanding on lowest common multiple. 80% of your kids get your check for understanding question correct. Is that enough for you to say, okay, I am going to now teach you the routine that requires that atom? Or are you going to say, no, I need to keep going until I've got 100% of you. So stop now, everybody. I'm going to now teach you lowest common multiple or whatever it may be. And now let me do another check. Okay, now I'm up to 90%. So I'm going to stop again and I'm going to teach it again. Because the biggest kind of kickback I get when I talk about prerequisite knowledge is we never get to teaching the new knowledge, because we never get to the stage where enough kids have got it. And my response is always be similar to what you guys would be thinking here as well. Again, you don't really have a choice. There's no point trying to build new stuff on shaky foundations. But is your percentage really 100%? For prerequisite knowledge, is it 100%? Or do you go a little bit lower than you would do when you're teaching new atoms?
Who do you want first?
Yeah, I don't. Okay, so you've got two options, and I've already mentioned them. One is, yeah, it's 100%. How can it not be 100%? If it's not, then you're essentially proceeding forwards, knowing that there are even one child in the room who can't do it. So what are you playing at? What are you doing? The alternative, but it depends. But no, it depends. Okay, so it's different from. It can be different from I'm going to teach we do worked example problem pair. There are still things that you can teach to the whole class where they can all participate, they can all be a part of it, which is partly what I mentioned right at the start with you can avoid the blocker. If the blocker is LCM, give them the LCM.
Yep.
And go from there. So so the difference now is there's a huge amount of optionality you have to set them problems, set them exercises, I should probably say, where every single kid can still participate so long as they follow what you're doing right now here in the lesson. Like if they're not going to attend, if they're not going to pay attention, do what you ask them to do. I mean, that's the deal, right? They have to do that, or else they're not going to succeed. But at some point, if you want them to do the full chain top to bottom, you need that one child, those 5 children, whatever number it is, to be able to do the thing you know they can't do. I just don't understand the world in which someone says, but we can't, I'm going to move on and leave those 5 kids behind and have them be eternally behind. That's not, sorry, I'll back up a little bit because that's not true. I do understand that world because that was most of my time in the classroom. So why did I do that? And if I think especially about my mixed ability year 9 class, my final year of teaching, I have this visceral recollection of 2 girls out of six very weak kids at the bottom of a 23 individual class and 6 very, very top kids. And there's always 2 girls that come back to mind as just persistently failing, constantly. And if I were a teacher then, if I were that teacher in that moment, and you came to me and said, no, you have to get those 2 girls up to 100% to join in with those kids at the top end of my mixed ability group, it's like, great, Craig, well, you take them. You sort that out, and then when they're ready, come back to me, because by God, the gap is a chasm.
Yep.
But the difference is, it wasn't until the very end of that year that I really sort of cracked a sizable amount of the whole unstoppable learning system, that those 2 girls were now able to come along for the ride. And that's the thing I blogged about back in 2016, I think, after you and I first spoke. My best planning on the old blog site. And that what was different? Why could both of those girls, one of them tracking level 2B the entire year, why can she suddenly solve simultaneous equations? Well, because I've narrowed what I'm asking her to do. All the equations involve addition. She can add single digit numbers. She can add a single digit number to a 2-digit number. She can do that much. And everything else was being taught relatively brand new. I just avoided all the things she couldn't do, and then taught all the new stuff according to these instructional sequences and this atomized way of learning, and chained it. We did 5 lessons, including some double periods, on solving simultaneous equations. We did not solve any simultaneous equations until the last lesson. So everything was built up and chained until we got to that moment when she could do it. And when we did do that, we didn't start with something silly like x plus y, x minus y, which is just about the hardest pair of equations you can give them. All the secrets were revealed. No secret ones. visible coefficients in front of the numbers. When you do it that way, it's actually fairly straightforward. So that's the difference. So I guess I come across so forcefully now because I know what is possible. I've seen what is possible. I know it can be done. But just to backtrack a little bit, most teachers in the classroom are not in the position that the three of us are in. They don't have this mental model for how to think and break things down and act and adapt in the moment yet. We're obviously all working to help as many get there as possible. So yeah, I get the pushback. Unless you have that mental model, you won't understand what to do, and you'll just feel overwhelmed by the chasm, by what those bottom 1 to 5 kids are experiencing. And there was one teacher I started with, the head of maths, a few months ago. We picked out his weakest kid in one of his classes, and he's a very emphatic, very enthusiastic, very smart teacher, and sort of properly bought into the idea of all the kids can and will succeed. But I do not know how to make it any simpler for this one boy
Yeah, yeah.
such that he can follow along. But again, his mental model of teaching was worked example problem pairs. I'm just going to very, very simply talk you through this example. Now you do one.
Yeah.
He's not getting it because he doesn't trust that if he just does what I say, he'll get it. It's like, it's not that. It's not atomized. There's transient information problems. There's prerequisite atoms in there he can't do. Once you start breaking it down like that, things do change quite rapidly, quite excitingly, I think.
Lee.
I had a few points to make. I think the first one I'm going to say is like what a lot of people will be feeling when they get asked this question, and I just think you are screwed if you even leave one. If it's not 100%, you have you just put another screw in the coffin of the fact that your class, by the time they get to year 11, these kids are that's gonna really be a melting pot of such a mess. Like, I've just written a few things here, like the sort of things that are being built by that one kid or two kids. Every question, if you're leaving one out, every question, that kid is building resentment, they're building anxiety, they're building their poor behavior, they're saying their complaints to their parents. You do that 5 times a lesson, 5 times a week. You've got 25 kids that have built resentment against you as a teacher and are not on board with the journey anymore. That translates into bad behavior. That translates into poor classroom culture. That degrades your class massively over time. I think that's one of the things I found with the 100% and always insisting on 100% is that my class is a very pure place. The kids are happy to be there. The classroom culture is buzzing, and it's not because I've done anything explicit to make that. I haven't sort of come up with some genius, I don't know, thing that we can put a cool name on and say, I did this and this is what built my classroom culture. But it's just built by the fact that no kid wants to opt out. And I think a good analogy I found for this is with my daughter. So she just never wants to do the wrong thing. It doesn't cross her mind. And the more you can make that never even cross their mind, so you don't ever have to deal with that, the best, right? And that's the best way I found to deal with that, is that most of the place where they build that kind of bad feeling towards you, even if they don't do it consciously, most of the time they just get a horrible feeling. You made me have this horrible feeling. It might not be conscious, it might not be rational, it might not be logical, but a kid is going to do that, and that is going to have a massive influence on your class. And I imagine a lot of teachers are feeling that. And I imagine a lot of the teachers that have problems like that in their class, if you ask them, do 100% of your kids get it 100% of the time, they would say no. And and I would struggle to imagine a teacher that gets 100% of the time with their classes would have any of those kind of issues. Interesting.
Think if
Oh, go on.
Well, I was just thinking, if that's how your daughter feels, you're going to have a lot of people coming to you for parenting advice before long. I just wanted to chuck in two things, maybe two, and then emphasize again something I've already said. One, the point about having no cool name for it. I mean, I call it the penny promise, a bit after my mentor Penny. It is that the ability to stand in front of the class and say, do everything I ask, pay attention the whole time. I promise 100% you are going to get this, every single one of you, no exceptions. And if at any point anything does go wrong, or you can't answer a question, or you get the wrong answer, etc., as long as you've done everything I say, my fault, not yours. It is my fault. I've done something wrong. And you know what? That's also okay. It's okay for me to slip up or for me to make a mistake like this. It always gives me new information I can use to ask you a better question next time. And so that's one thing. The second is, I think everything you're saying probably about the resentment and the anxiety building up is true. But I also couldn't help just this tiny, tiny alarm bell at the back of my head flashing back to 2011, 2012, when all the rhetoric in all the schools up and down the country was one of complete abdication from senior leadership, where they would say, from the state level on down, everything was saying, if lessons are well planned, kids will behave. That was the logical
Mm,
chain of thought. Therefore, if kids are not behaving well, the lesson has not been well planned. It's your fault, teacher. And I have to strongly push back against that. So I just want to flip a little, even though I think what you're saying is correct, actually. I think it's true, and I think it's good to hold it in mind. I also want to flip it a little bit and say, well, just imagine the classroom where actually in every single lesson, every single day, yeah, 100% of them are always getting it. They come to their maths lessons and they know today, whether I like it or not, I'm not going to be confused and frustrated. I'm going to get it, and I'm going to get the ticks, I'm going to be successful, and I'm going to learn maths, and I don't have to become one of those people who says, well, I never got maths anyway. Um, every single one of the 100 kids you teach that experience every single day. How exciting, how invigorating that is. And that is the feedback we keep getting from the teachers we work with. Again and again, within a month or two, that feedback starts, and then it is pretty resounding after 4 or 5 months. Um, and so, yeah, and so I did want to re-emphasize. I mean, I've kind of already hinted at, but I wanted to re-emphasize again. It's so easy for us here right now, especially you and me, Craig, who aren't full-time classroom teachers right now, to say, no, no, it's got to be 100%. But I do want to stress again just how hard, it's not even difficult, it's just impossible. It seems impossible for that to be the standard, for that to be the expectation on a teacher when they have not been given the tools to achieve it. I think that is what happened with the whole behavior for learning movement around the 2010s was this expectation of good behavior in classrooms, but teachers weren't given the tools they needed to achieve it, which, as Tom Bennett will tell you, as we achieved at King Solomon Academy, has to begin with the senior leadership and the structures the senior leadership put in place. And then you can place an expectation on teachers to use the tools to achieve that successful behavior. Well, similarly with the whole 100% narrative, it's one thing to say it, but just exhorting high expectations isn't going to get you there. We have to give teachers the tools and the whole system so that they can see it and see how it works for themselves and believe it, not because we exhort them to or some sort of act of faith, but because they can see how obviously A will lead to B will lead to C will lead to success for every single child. So on the one
can I
hand,
make a
yes,
point?
the answer to your question is 100%. But at the same time, I wanted to step back and just acknowledge that for a lot of teachers in a lot of classrooms, that probably does feel impossible right now. And I think it is impossible without the right system of instruction in place.
Lee.
Yeah, just quickly, I think you are so right. Because I would have been on the opposite side of this debate 2 years ago. I'd have been like 100%,
Yeah,
you're joking. Don't be
Yeah.
stupid. I'd be like, you're absolutely ridiculous. You're living in fairyland. You're an SLT person. You're someone far removed from the classroom that doesn't have a clue what it's like to actually teach a lot of these kids. Before I had exactly those tools, before I'd practiced and I'd learned and I'd expanded myself and got myself to that point. And I sorted that out, and I've been lucky enough to have good people teaching me and improving giving me those tools to be able to do that. But yeah, I completely understand that most people don't. And the issues that most of these teachers are facing are completely outside of their control. And if you're angry at the system and you're saying I cannot get to that point, then right now you're probably right. You probably don't have the tools to get to that we want right now, but that's where the work comes in. I mean, that's not work for you. That's not all work for you. That's work. Every person in the system has to take responsibility to some extent, but it's not all work for you. It's definitely not all work for you. It's not all your responsibility, and it's not all your fault if that's not what you're experiencing right now. I think that yeah, you're completely right. That's so important to say. One other tiny thing, sorry, I wanted to say on when you were saying about getting to 100%. If you've properly spaced things, then likelihood is you're going to be getting 80% of your class. The first question that you asked. But I have no issue with having to ask a couple of questions before you get to 100%. So I don't expect to get 100% in that very first question. I know who's going to struggle. I'm going to be standing behind their whiteboard watching their exact thought process because I only need to look at 2 or 3 kids in the class. I know what's going on in their heads. I can see the loops. I can see where they stopped writing. I can see where they started looking around the class. I get it. That's the thing. Solve that one thing. 2 questions later, everyone's on 100%. I move on. Yeah. So that can be solved, I think, quite quickly. it doesn't just have to be through one question, and you can, most of the time, if it's been spaced properly, if you realize that it's some deep fundamental issue, they don't even know what a negative number is, then I completely understand. And most of that time just comes down to that it hasn't been taught properly throughout or spaced properly throughout, and maybe you've taken over at a certain point, and the previously that they haven't been quite, I don't want to say taught properly, but taught very well to the point where they can't remember it. And it is a fundamental issue that does really need to be solved, and it's probably going to take some time. But if it has, then most of the time it'll be very quick to solve, and you get to 100% very quickly.
I think that language of 2 years ago, I would have been like, yeah, 100%, you're living in fairyland. Interesting connection for me. Just yesterday, the teacher had reached out and we had a conversation, and I'd asked if he had support from his head of maths or had senior leadership in the school to maybe work with us or implement what we're doing. And his initial response was, well, I spoke with the head of maths at the end of last year about this, and he said it all sounds like nonsense to me. And so I drilled into that because I thought, oh, does he object to this way of teaching? Maybe he's still in the very sort of inquiry, child-centered mindset. And it turns out no, it was just the 100% language. He was just, no, that sounds like nonsense. That's fairyland. So fair enough. That is still big and prevalent and out there. And then I wanted to re-emphasize what you said about not expecting to get 100% with the very first question, because I think maybe I've been misunderstood with this sometimes, and people are expecting 100% of kids are getting the right answer to every 100% of questions, and it's not that. And actually, in the second session that we work with, when we work with teachers directly, I share with them a video of a lesson where I was working with this this class of kids who were outside of mainstream education. And sure enough, you see X% of them get it wrong first time. And then it's a much smaller percent get it wrong the second time. And then the third time, 100% of them have got it. Then we maybe try another one. Then we move on to the next thing, which builds immediately on what they just saw. So it's all sort of carefully structured. So they're still practicing, but probably the new gap is small enough. So it's not 100% correct answers to 100% of questions. It's 100% success, every single kid getting there, essentially.
Love it. Right. Okay. So here's the plan. What I'm going to do, I reckon we've time to tackle one more question. You'd think in a podcast we could do 6, but we can't, because these are deep questions, and there's 3 of us, and we don't like to. We're pushing for 100% ourselves, right? We want to get 100% of the things that we wanted to say to each thing before we move on to the next. So what I'm going to do is I'm going to tease 2 of the questions that we're not going to cover today, just to hook listeners back in when we resume for episode 4. And I'm going to selfishly choose one of my questions to end with, because I want to know the answer to this. So we're not going to get to Jordan's second question, but Jordan, we're going to cover this first, episode 4, I promise, which was how much wait time and prompting do you give students to ensure they attend to differences between examples and non-examples? Great question. That's coming up, episode 4. And then I want to do a geeky deep dive into stipulation, because I read one of Kris's posts on this, and he shared a sequence of questions, and it would examples and non-examples, and it was very different to the one I had in mind. So I want to dig into both Kris's thought process and Lee's experience with how do you decide which features of category atoms to include in an MPPPN and which ones to leave out. So that's all coming to an episode near you in the future. But I want to end with a question that's been bugging me for a while, again based on one of Kris's Substack posts that I read. And that's to do with overtization, overtizing the steps of a routine. So what I want to do, Kris, I thought this would be a good way to pitch it, because I think we disagree on a fair bit here, but I'm interested. I'm going to tell you what I do and why I do it. And then I want you to draw the similarities, the differences, your reasons for it, and then hand over to Lee to get his thoughts, if that's all right. So let's stick with adding and subtracting fractions, and let's imagine we've done the atomization. So we've broken it down, we've identified a few atoms that kids have met before, and we've checked their understanding, and we've got it to 100%. The kids are loving lowest common multiple. They are amazing at adding fractions when the denominators are the same. Everything's looking good, right? We've then also identified a few new atoms. So one of those atoms might be identify when a pair of fractions are in a form ready to be added and subtracted. So we've covered that as a category atom. We've done a nice MPPPN. So now kids, they are the world's leading experts at knowing when they need to transform an atom or not. Basically, all the atoms are there. All the prerequisites are there. All the new atoms are there. So now we're ready to introduce the routine of how you add and subtract fractions when the denominators are different to students. So this is where I'll say what I would do, the kind of two phases of this, and then I want to get your take on this. So this is where I would kick in with a classic I do, where I would demonstrate from start to finish the steps that the students would do to add or subtract two fractions where the denominators are different. And typically, I would do this in silence first, very, very quickly, and then I would narrate each of the steps, and I might do a couple of checks for listening, so just get kids to repeat back key bits of it. But this would be very quick, maybe 30 seconds, 45 seconds, something like that. It certainly wouldn't be one of those I do's where I'm asking kids to speculate what step comes next and blah, blah. I'm not doing any checking for understanding. I'm just trying to convey as clearly and as efficiently as I can the order that these atoms that are very familiar to the kids fit together. And I just want a bit of data as to where the kids are paying attention. And then I move into a we do. But my first we do takes a very specific format. And I wonder whether this is the bit where I wonder whether it's similar to your idea of, or Engelmann's idea of overtization. Because what I want to do now, I've already checked that kids can do each of the atoms. They're secure with that. But what I want to check now is whether they know the order to put these atoms together. So I do what I call a step-by-step approach to the we do. So I'll say to kids, okay, here's a new problem for us to do. Let's say it's, 1/7 take away a third or whatever it is. On your mini whiteboards, write me down just the first step to solve this problem. Not step 2, not step 3, just what's the first step? Hover 3, 2, 1, show me, bang. So now I've controlled the flow of information. I've only got one thing to look for on the boards. Let's have a look around. 100% of you have identified that these fractions are not ready to be subtracted. That is step 1. Amazing. Right. Now, write me down step 2 on your mini whiteboards below that. Hover 3, 2, 1, show me. So I get to collect data one step at a time, reducing the flow of information. And my aim of that we do is to check that students understand the order or can recall the order that these atoms that they're completely familiar with fit together. And when I read your post on overtization, I thought, the other thing that I'm doing there is I'm making the steps of this routine super explicit to kids. There's nothing hidden there because we are literally breaking it down one step at a time. And from a diagnosis issue, to go back to one of Lee's earlier points, if kids go wrong, I know exactly where they've gone wrong in the process because I can see it on their mini whiteboards. So just to reiterate, after the atomization process, when I come to teach, in inverted commas, the routine, it's a teacher-led I do, often done in silence with a few checks for listening, and then it's a step-by-step we do on mini whiteboards to check whether kids can follow or can recall the order that these atoms need to fit together. So, Kris, over to you first. What are the similarities and what are the differences between our approaches when we get to that stage where we are about to show the kids how all these atoms fit together to teach a cognitive routine?
You said you thought there'd be a lot that we would disagree on. What kind of things did you imagine we might disagree on here?
Well, I'll tell you exactly what. I don't think you start, I think you start, there's certainly a bit in your book, and also I think I'm right in saying the start of your Substack post on I Do, We Do, where you essentially come out and say, I Do, We Do is an effective way to teach students routines, but it's not the be all and end all. Whereas I love an I Do, We Do to teach a routine as long as the atomizations come first.
Gotcha. Okay, so for both of those, I think the first thing I would say is true. So I've got a big picture, then I'll bring us back in. By big picture, I mean in sort of everyday conversation, I hear people say things like, scientists are always changing their mind. Scientists have always got it wrong. And then they'll quote things like, scientists used to think the world was flat. Or if they are a bit more knowledgeable, they might talk about phlogiston theory, or the theory of phlogiston theory was the idea that things ignite because there's a combustible substance inside them, which is called phlogiston. Or the theory of humors, where the idea was in medical science, there are 4 colored humors in the body. I can't remember them all. Bile was one of them, different colors. And you're in good health if the four humors are in balance. So there's these ideas which have been held throughout history and are sort of pseudoscientific. They're pseudoscientific because they are usually just that. They're ideas people had, and they were never arrived at via a scientific method. Conversely, I mean, maybe there are some, I'm not sure. I'm not aware of any strongly held scientific theories post about the 1600s-ish, things that have truly been devised via the scientific method that have been completely thrown out. So my favorite example is mechanics. Now, how do things move and why? If you go back a couple of thousand years, Aristotle said, well, if you push something, if you apply a force, it moves. If you stop applying a force, it stops moving. And that's a very, what do they call it, folk science understanding of motion. And you probably learn in school that, well, actually, if the reason it stops moving is because of an opposing force from air resistance or friction. If you were in space, it would go on forever. And we've now internalized that thanks to lots of sciencey films and TV series. Um, what did Newton say? Newton said if you apply force, you get a proportionate increase in acceleration. So if you remove the force, you don't remove speed, you remove acceleration. That that is true, but it has been superseded by Einstein's ideas around relativity, where he basically said, yeah, that's true up to a point. And actually, as your speed approaches light, you don't get as much acceleration anymore. And as you get really near to light, you get basically no acceleration, no matter how much force you put in. Now, what's interesting about that is Einstein's theory there is much more general, much more comprehensive than Newton's. But if you swap out your speed that you're traveling at from something near the speed of light to 20 miles an hour down the road, in the equations, you get Newton's exact same equations. In other words, Newton wasn't wrong. He was just looking at a very narrow scope. So now to bring this back to our example, because I find this quite exciting. I think with things like I do, we do, and I did try to stress this a bit in the posts, and also with what I understand about your step-by-step thing, I don't think there's any disagreement because I think both of them were hinting at a broader picture. They're like Newtonian mechanics. They're a small part of a much more general theory or general system of instruction, which Engelman obviously has possibly given us as the most generalized version I'm aware of. So everything you've described with the step-by-step approach, I would agree with. I do, we do, I agree with. It's just I agree with in the same way that Newtonian mechanics works for certain situations like small speed, those techniques work in certain situations. If you try to apply them to every situation all the time indiscriminately, then they either might not work, like your example of I spent 6.5 minutes watching somebody try to teach how to use the sine or I think it was sine rule or cosine rule. Worked example problem pair, 6.5 minutes, he lost the kids, massive transient information loss. Yeah, it doesn't apply there. And I think that's probably where we're at right now. We're at the point where those ideas are out there and they're good, but they're practical ideas. They're practical ideas that are based on theory. The theory is less well understood, and you need the theoretical understanding to realize how you can adapt it to a broader set of situations. So it's exciting because we have something that we don't have to throw out. We don't have to throw out I do, we do. We don't have to throw out worked example problem pairs. We don't have to throw out the step-by-step approach here. What we get to do instead is build on top of those ideas with increasing nuance, increasing incision. So with that said, then, how is what I would do, or how is Engelman's overtising when it comes to overtising steps a bit different? It just offers more options, I suppose. So you described one option, which is I've now taught the atoms. I'm now going to teach the full chain. Before I do, go through it in one big go. I'm going to get the kids to do it one at a time, step by step, so that they both understand the steps more clearly, and so that I can see whether or not they're getting each step correct. So that idea of them understanding the steps a bit more clearly, it wraps up with Doug Lemov's idea of name the steps. That is a technique in Teach Like a Champion. It's closely aligned. Again, a part of a much bigger, more comprehensive picture, I think. What does Engelman say about it? First of all, with overtization, he's trying to make overt two things. Thing number one, what is going on in the kids' heads? Thing number two, what is going on in the teacher's head? So so what's going on in our heads is invisible. It is covert. He wants what's going on in our heads to be overt, revealed to kids so that they can understand what we're doing. He then wants what's going on in their heads to be revealed, made overt, so we can see whether or not they've got it, which you've kind of latched onto a little bit yourself. And he just with that sort of idea underpinning everything, he's then got multiple different ways of dealing with this. So Engelman goes as far in his programs to let's say you were adding fractions, you might start with okay, put your finger on the denominator of the first fraction. And then the next thing is, what number is your finger pointing to? So those two steps, we would never ask those two questions ordinarily when getting kids to add fractions. He does it, or something like that, with very low level ideas, because he wants to make sure every kid is pointing at the right thing when he says denominator of or thinking about the right thing when he says denominator of the first fraction. So the way he gets them there is get them to physically point at it, and maybe he can just see it. But if you just whip around, are they all pointing at the right thing? If not, now that they're pointing at the thing, so their attention is directed at this thing, what number is your finger pointing at? Great. Now the next one, and builds up from there. So that's like the first idea, very intentional about revealing what's going on in their heads, what's going on in your head. The second, then, he has this explicit concept of covertization. Naveen Rizvi wrote about this extensively 8 years ago, I think, on her blog. I think she first popularized this possibly. So when the way you described it was you've identified a practical problem in the classroom, and I love the post you've got on this. You can see the whiteboards and you can see, oh my God, yeah, how am I going to ascertain whether or not the kids have all got it or where they're going wrong? So you've identified a practical problem and a practical solution. Let's just do it bit by bit. What Engelman is saying, which I think takes it to the next level, is okay, we're breaking it out, we're overtizing it for these reasons, but we obviously don't want that to be our end position. We don't want to be constantly going through this line by line. So how do we get them from do this and then do this and then do this and then do this to do this? And that prompt initiates the chain of all of those atoms one after the other sequentially. So he now has routines for covertizing. So he might start off with, it might start from exactly where you described, do this and then do this and then do this. But then he's got sort of procedures for efficient covertization. So having practiced that a bit, the next thing might be a little bit less over. He starts to covertize a bit. So he might say, do this and then do this. And then you show that on the whiteboard. Okay, and now do this, and now do this, and now. So two of the atoms become one in the set of instructions, as an example. And then you might start combining more of them in the set of instructions. You might say, if we take the example of expanding brackets, because it's small enough to handle, expand a pair of brackets, expand the first bracket, then expand the second bracket, then simplify like terms. So you're saying three things all in one. But what we want to get them to is expand and simplify. So at some point, you have to introduce this, or expand and simplify fully. So at some point, we need to introduce the language and have it be clear to them what we mean by that language. So at some point, we may have to say, okay, when I say this, I mean do this, and then do this, and then do this. For example, my turn first, do this. Bum, bum, bum. Your turn, do this. And you've just tweaked one thing in the example for them to do. So I think that's the biggest difference. So I agree with what you said. There's nothing I disagree with. I think it's great. I don't think there's anything Engelman would disagree with. But in my reading of theory of instruction, he then takes it further and says, well, we now need a protocol for efficient and effective covertization so that we can eventually just give them a prompt and they can crunch all the way through 15 atoms in a chain for 4 minutes to solve this sine rule problem with the triangles. How well have I answered that question there? Because I
it's
went big and
interesting.
then came in.
I'll come to Lee in a second. Yeah, I think that's really good, mate. I think the thing I need to get clear in my head is I think I'm almost taking for granted. I think I'm all right with the overtization. I'm kind of then assuming some magic is going to happen that then kids will be able to do it themselves without the kind of routines for the covertization. I don't think I've thought hard enough about bridging that gap. So the step by step is obviously very, very structured. And then following that, I do a second WeDo where I move into Adam Boxer's tick trick idea, where I give the kids the initial prompt and they have to then do it all on their own. They do it in their books, and I then allocate ticks. Tick if you got this bit in the right place. Tick if you got this. Tick. I've spoke about this on with Adam, in fact, a couple of months ago. But maybe that's too big a jump. Maybe I need to be a bit more explicit or a bit more considered about that transition between the really overtized step by step, and then maybe that it's a bit too. I haven't supported them enough to then just get from that initial prompt right down to the end. Maybe
only if anything less than 100% of the kids are successful. If 100% of them are successful, what you've just described is probably a lot more efficient. So you never want to over atomize or overtize or go too slow with the covidization process. And it's one of those things which I think is frustrating for a listener, because the question is always, what do you mean by over atomize? What do you mean by do it too much? And the answer Engelman actually gives is do less rather than more.
Mm-hmm.
Because if you do atomize extensively, if you do overtize steps extensively, and all the kids get it right, great, but you don't know if they could have gotten it right faster.
Yeah.
So if you actually do a little bit less, maybe take a risk, allow some of them to get it wrong, at least you now know for sure you need to overtize a little bit more or atomize a little bit more. And you're prepared for that, so you can even adapt on the fly in the ideal scenario. So that's how you would do it. So and so the only reason I would agree and say, great, think a bit more about the covidization protocol is in the condition that you're encountering children who are still not getting it right, even after you've gone through that. If they're all getting it right, don't need to change anything. If they're not, then having thought about these things gives you the next thing you can do. And that's what I mean about some of what's out there right now being a smaller part of a much bigger structure, system, theory of instruction.
Love it. Lee, over to you.
Yeah, I love what you were saying there, like finding that sort of boundary. I just wrote, I like making names. Finding that boundary of efficiency, like the point at which you lose people. So I think going below 100% is now for me is so valuable. Like if I drop below 100% in the class getting it right, I go, ooh, we've hit this boundary. There's something here. There's something here that needs to be, mined and excavated, and we need to go into it a little bit more. It's a bit of fun. But yeah, just finding that boundary. If you play it too safe, then you can end up doing it well and doing it properly, but doing it way too slow that you're not even being as effective as you could have been. So it's all like that sort of balancing act, isn't it? So, for example, I don't think I would go step by step in the same way as you, Kris. It might just be the sort of classes I've taught, or it could be anything. I don't think either of us are wrong in that, because I think yours is a bit safer, and you're going to be more 100%, and you probably run into less problems, but you might be less efficient in some places.
Yep.
And I think that is kind of quite a beautiful thing to get down to that, where there is no actual better, in my opinion. It sort of comes down to this of, I'm being a little bit more risky, and I might find a more efficient method, and I might find that they can do it with slightly less instruction than they needed. But then you've got that safety of, you're not going to run into those unexpected issues, and you're not going to have those kind of misunderstandings that may come up. And I think that is just a compromise. Like I don't think there's a very clear winner there. So I think that's quite nice. For example, with the routine, what I've been doing this year is just pretty much just telling them. It's just that you do all the transformations, and I just talk them through it in words, like not specifically talking about the numbers that are in there. So like first I might say, first I want you to find the total parts of the ratio. And I'm talking about it properly, explicitly with normal language. I'm not talking about it with math, like explaining specifically in that question what I want them to do. And they can follow that, and then you fade the scaffolding at time, and you say, okay, guys, what's the go on? You can do the first step, and then I'll sort of guide you through after that, and then maybe you go to specific people, and you may need to say, the next step is this to that person, or they might need a little bit of help on the last step. And the better you get to know your kids and the more you can adapt on the fly, and the better you get at that sort of whole process of instruction and knowing who's going to struggle where and what sort of advice they might need and what push this kid might need. That's where the art of being a teacher comes in, I think. And you just sort of you get to play around with that. So yeah, I found just telling them and then just observing and going from there. It's just the versatility though. I think that's the thing that it comes down to. Like, I have so much versatility. I have so much versatility. Like, I put that out there. I've asked them to just do this with the words that I'm saying. If I now walk around and 10% of them are getting it, then now I've got the choice. Now I can go a bit safer. Now I can go a little bit safer. Now I can say, okay, all right, everyone, now I'm going to do what Craig says. I'm going to say, everyone, first step on the whiteboard. And I'm going to very explicitly find where this is. But yeah, as I said, you can be versatile. You can swap between your method. You can swap between my method, right in the middle, because they've been taught those transformations to begin with. That knowledge is sort of, it can be moved about, it can be changed in different ways, and it can be played with. Yeah.
It's a real interesting one. A final thought for me on this is, so I'm boring, right? So I absolutely love a structure that I can do time and time again. So if we take the kind of atomization, teacher-led I do, first we do step by step, second we do tick trick, right? I'll tell you 3 reasons why I love that, right? So the one is I get better at it each time I do it because I know the routines, I know what I'm going to be doing, I know how to introduce it, blah, blah, blah. So I get more efficient. Secondly, the kids get used to it, right? The first we do, I know what we're going to set out on our boards. We know he wants us to write nice and big, that first line at the top of the board so I can see it. Then he's going to ask us to do the second. There's no point in us trying to look at our neighbours because we've done this before. There's no high stakes. There's no embarrassment attached to it, blah, blah, blah. Tick trick, we know to set it out neatly in our books, blah, blah, blah. We know exactly. So the kids get better at it each time. But thirdly, perhaps thinking from mine and Kris's perspective here as 2 people who work a lot with teachers, it's really interesting, right? I completely see your point, Lee, there, that versatility is a real potential strength of a kind of philosophy of teaching or a way of teaching that you can adapt and stuff on the moment. But for a lot of teachers, particularly novice teachers, less experienced teachers, it can be a real drawback as well, right? Because you just get overwhelmed by choice. What the hell am I supposed to do here with this? Whereas there's quite power in kind of constraints, simplicity. All right, I'm always going to do it this way. And then when I get better and I get more confident and so on, then I can start to take a few risks. So I just wanted to, kind of pull up that point that I think that often there's power in routines. And in that particular routine, I found the atomization, teacher-led I do, step-by-step on mini whiteboards, tick trick. I find it quite a nice kind of quadrilogy, if that's even a word, of things to do to kind of get kids, after the atomization, to get kids get good with the routine.
I love it. I think you've got a brilliant process, and I have used your process. I have used that almost that exact way of doing something, and it does work. It's absolutely brilliant. I think the nature of working in a school where you have 31 to 32 kids, I think most kids are going to sit somewhere on that spectrum, from your very, very structured approach to my very, very, what do we call it, versatile sort of approach. Every kid is going to sit somewhere on that spectrum as which one is the most optimal for them. And every teacher is going to sit somewhere on that spectrum as to which one's most optimal for them. And because we have 32 kids in the class, honestly, and it doesn't sound nice to say, but it comes down to just a sort of luck. Do you line up? Does the teacher, what works for the teacher mostly line up with what works for the kids mostly? Yeah. Because there will be kids in a class that will be doing my method, and you're completely right. They would say, I would just prefer to have this nice, clean structure that I know is going to be every time. I'm going to get the presentation right in my book. I'm going to be happy. It's going to look great. I'm going to feel brilliant. And then there's going to be some people that might be sitting in your class saying, oh, I could have done this a lot quicker. I would like to have been a bit challenged a bit quicker. We can get through 20 things when we actually only got through 10. And it is just kind of luck of the draw because you've got 32 kids. I think if you had one kid in front of you, you should do a bit of a diagnosis and work out what works best for them. Where should you sit? Do they need a little bit more structure, or do they need a little bit more versatility? You just don't have that luxury. You just really don't have that luxury, and I think it really does just come down to style. And the thing that you can control is yourself, right? And you might not know what is the perfect blend of structure and versatility for a specific class, but you know what's right for you, and you know what you're better at. So that's the thing I work on. I know I'm better in that kind of versatile environment where I can, if I train myself to be really good, then I can react on the fly. But you work better in a more structured environment where you can practice this one way of doing it and just be an absolute master, an absolute perfectionist at that thing. And you know that, and that's something you control. So that's the right way to go for you. And I think that would be good advice for most teachers to say, knowing yourself, because you can't know the kids that are going to be in front of you 100%. And working out the blend of 32 children is basically impossible. But you can know what you're better at, and you can know where your skills lie. And yeah, use that to judge where you should sit on that spectrum, I would say.
Just before I hand back over to Kris for a final word, he's annoyingly, isn't he, right? I was talking to him off camera. He's 29, right? And I'm trying to think I knew nothing at 29, right? And he's coming out with all this. It's annoying. Kris, you shouldn't have introduced him to the show. He's making me feel bad here. Well, we'll cut him. We'll cut him in future. Get some oldies on. Kris, over to you for your final word on this.
Please don't cut me. I'm having a great time.
Yeah, 29 definitely wasn't able to do what Lee could do at that point. I think the thing that comes back to my head is the idea that teaching as a profession is not yet mature. And this is an important and sometimes difficult conversation, I think, to have, because on the one hand, we have status and ego attached to the work that we do. And so we want as teachers, and we want teachers to be treated with the same authority and respect as other mature traditional professionals have been. Our professionals within a profession have been. At the same time, if it is not a mature profession, and there are things that could make it more mature, better in some way, better structured, then we also want that, but we're not going to get it unless we complain that things are missing. And so, what are some of the things that are missing? I think certainly historically, training was abysmal. When I went through training in 2011, it was borderline non-existent. I was being asked to review papers on social sciences and social theories of what the education system values, and was giving little to nothing on, here are things about mathematics that you are going to have to teach kids. Here is how you can teach it. And the few things I was given about how to teach it never ever worked. They were very idealistic, as if they were never tested in real classrooms, and yet were being pushed onto teachers by people who were no longer teachers or had never been teachers. So that is a whole mess right there. But the other thing that was on my mind that brought this to mind now was, I think you're absolutely right, Craig, that if you are new to teaching, in particular, perhaps even new to some of the things we're talking about, you want it to be very simple, you want it to be very structured, you want it to be routine, do the same thing every time. When talking about the different types of instructional sequence, things that you and I have talked about, Craig, include the comparative sequence. If you look on the Unstoppable Learning website, it lists only 4 elements, and one of them is not comparatives. I essentially pulled that out from the frontline messaging because it doesn't crop up that often. Where it does, it is essential and powerful, but it doesn't crop up often enough that it's worth giving teachers brand new to this a whole other thing to think about. So we just say, just let's not think about it, and we'll introduce it as needed later, further down the line. So I think that is very important and very powerful. And actually, if you can get teachers to be confident and capable in some kind of routine like the one you've talked about, or I mean, I started the book with a very similar point, that there's nothing particularly charismatic about what I do. I go in and I do the same thing every time, and that is what makes it so fast, so quick to plan and prepare, borderline effortless these days. It's the same thing every time, doing the same thing again and again. But it also because that's so effortless, that now allows me to get into much more naughty and nuanced things. It gets me to test the boundaries of it. I had somebody ask me on, so we've just opened up the chat feature for a couple of months on Unstoppable Learning Substack. And straight away somebody asked, I don't know how to do this for, I'm struggling to do this for getting kids to estimate the correct units to measure something. Like, why do you use millimeters, centimeters, and meters for the width of an ant versus a person? And for me, it's like, oh yeah, that is, I'm a bit unsure about what to do with that as well. But it doesn't take me long to realize why I'm unsure and then what to do about that, which I was able to offer him in the response. Most teachers don't need to worry about that. That's such a niche part of the maths curriculum and the maths exam. It's not going to come up very often. Um, but you'd want, because back to the profession point, a structured profession would be able to say, look, when you join, you're at this level and you're doing this thing, and your job is just learn how to use the tools you're given and use them really well in a predictable, systematic, routine way that allows your life and work balance to be pretty straightforward, that allows you to get pretty damn close to some version of 100% success for all of your kids. Um, and then that's great for the next few years. And then once you've been doing that for a few years, you might start wondering, wait, is there not more to this? How do I engender a greater passion for mathematics in my students? How do I get them to maybe um, understand a bit more what it is to be a mathematician outside of school, etc.? And you've got loads of headspace free, a bit the way Lee was describing there, to start thinking about those things and learning about those things. And maybe that's the next level up. Maybe you stop being interested in just delivering the materials and tools you've been given, and you become interested in being a part of the teams that refine these materials and make them even better. Um, it's a podcast interview I saw with Nick Gibb, who's Teachers Talk Radio. Nick Gibb was on there a couple of days ago, and the challenge they put to him was, it used to be teachers had no autonomy, local authority tells them what to do. Well, now today, in some of the trusts, it's the same thing, isn't it? The trust tells them what to do, and they just turn up with branded PowerPoints, etc. And I think a point Nick was trying to get across, Sir Nick, we should say, that didn't seem to be landing for them was, it used to be the case that you'd have people in local authorities that were telling you what to do based on spurious ideas,
Yeah.
spurious theory, sometimes perhaps not even in a classroom for the longest time, and no kind of mechanism to intervene or feed back up the chain or be involved in the process. Now, sure, for a lot of teachers, it might well feel like your hands are a bit tied in the classroom in some trusts. You're told what to do. Here are your branded PowerPoints, etc. But usually in those trusts also, like, fine, you've got 100 teachers, you need consistency. But part of what they're being provided is based on much more theory and research now, is likely to be much better than what you might have been given previously. But then also, trusts will have or certainly should have, the mechanisms for you to be able to feed back into that process, or maybe even to join the central trust team and become one of the people who creates those and modifies them in the future. So there's still something in the teaching profession, when I say it's not yet mature, where it seems to be you get dumped into this category of teacher, and then your career progression is either weird, like you go off into random directions all over the place, like certainly you and me have Craig and Lee might do in the future, or you follow this tradition of, I'll become head of maths department, then I'll become a senior leader where a big part of my job has nothing to do with maths teaching anymore and is related to a lot of things that have nothing to do with teaching at all. Then I'll become a head teacher where even less of my job has anything to do with teaching anymore. Or I'll even possibly join a central trust where, as one person suggested recently, a friend of mine, he's increasingly feeling like CEOs of trusts not only certainly don't need to be previous teachers, he's thinking, but maybe even often shouldn't be, just because the things that the CEOs of trusts are thinking
Yeah.
about are so far removed from classroom teaching and subject and academic excellence that it kind of doesn't matter. You hire a director of education or something similar, or a chief standards officer, as Colot has, and they'll take care of that. And the CEO thinks about a different thing. So it's not clear what the teaching progression is yet. How do you become a better teacher? How do you go from the lowest levels to the highest levels of what it is to be a teacher? What is the trajectory? And I think this was a big conversation in 2013. It was my first talk at Wellington at the Festival of Education, was on whether teaching should have a codified body of knowledge. And then, I don't know, it just seems to have disappeared. I think because institutions like Matt Hood's Institute for Teaching, which then became Ambition, sprung up. There's the new National Institute of Teaching. There's the Royal College of Teachers has sprung up. I don't know. From the outside of the classroom looking in, I don't see that it's become clearer and more structured. And Nick contrasted it with what his experience of was as an accountant, where it's just really clear. You go in, you're told exactly what to do and how to do it in the beginning, and then there's this very clear progression ladder from there. It's the same in management consulting. It's the same in the medical profession. It's the same in lots of other, what we might call mature professions. It's the same in the legal profession. Tell me if you think I've got this wrong, Lee, because you're in the classroom right now. But from the outside looking in, I don't see that there yet. And so we end up with this disparity where, Craig, you've got one way. I'm going to be very structured and routinized, especially when I'm speaking to teachers. Lee, you're shooting for that kind of master teacher level, and you're thinking, no, I want to know it all, have the big theory in my head, and I'll routinize as needed, and I'll adapt on the fly as needed. And it would almost the conversation treated it as you do it your way, I'll do it my way. When in my head, it should be a bit more like, well, you start at one point and you progress. I think that ability to be adaptable is probably the apotheosis, but yeah, it's the progression at the top end of becoming a true sort of master of the craft, as it were. So
Now, yeah,
that's how I think about it.
I had two things that can I say quickly.
Yeah.
One, completely right. In terms of progression in teaching, it's a complete mess. Like I pride myself. I care about teaching. I care about my kids. You know, I read and I learn. And I expand my knowledge, and I'd like to think I'm quite a good teacher. But I have no desire. The only desire I would have to be promoted past pretty much where I am as a lead practitioner, who is still, in my opinion, the only job that is sort of on that vein of what you're saying, where I have a promotion, and you know that is. It's a promotion of the quality of my skill and my art, not a promotion based on completely other unrelated things that I may or may not be good at. You know, going into being head of maths or being a senior leader or a head teacher. So yeah, it does feel completely messy. Like I wouldn't want to make the next jump. The only reason I'd want to do it is purely out of morbid curiosity. I want to know what it's like to sit in the SLT meetings. Honestly, I have no. It's not even that I have any bad feeling towards those kind of jobs. I just have no idea. It's just completely opaque to me what that progression is. It doesn't mean anything to me. Whereas I hear lead practitioner and I go, okay, yeah, that makes so much sense. You know, I'm going to be in the classroom. I'm going to look in other people's classrooms. I'm going to give advice. I'm going to improve teaching. The idea of being a senior leader is completely opaque to most people, and it just means nothing compared to your craft and your art. The only other thing I wanted to say was about the idea that you were saying that kind of idea of being versatile is the optimal that you're aiming for. But then you two, as your role in education is about sort of teaching teachers. If imagine there's sort of 5 levels of teaching, you're aiming at making sure that level 1 and 2 is sorted and done properly. James, my head of maths, likes to call me the pathfinder of the department. He says, oh, you're the one that's sort of aiming for that promised land. You go and find it, all right, and then you tell us when you get there. You know, you try these things, you practice, you become better, and you improve yourself, and you get to that point, and then you can come back and show us where everything is. And yeah, the profession needs that. I don't think we really have that. I think that's really the problem. I think we focus so much on level 1 and 2, and we focus on getting those teachers to be half decent. That where is that pathfinding? Where is that level 5? Where how do we get there? I have no idea, which is why I'm trying to learn it myself. And me and James are trying to find it, and obviously you two are part of the journey of trying to find that kind of the optimal way of teaching. But yeah, it was the difference in task between me and you, I think, there as well, Craig, of one being sort of optimal in the grand scheme of things, because you know, being versatile, being able to use your method, this method, this method, this method on the fly, very, very difficult, probably a very long way off of that, but probably optimal. But yours is certainly optimal for learning. As you've said, you strip away things to make it as intuitive and understandable as possible and in the most efficient way. Yeah.
Good stuff. Good stuff. Well, we're gonna have to put a finish on it there, because I've got a dull meeting that is going to be no way as stimulating as this conversation. I'll tell you what, Chris, I feel bad about this, right? Because we were just saying we're going to cut Lee because he's too young and too smart. We are actually cutting him for the next episode, right? Because we're going to introduce another guest on there who's involved in some resource creation. So as another little teaser, next month, we're going to have a guest who's been working with Kris on designing some example, non-example, and transformation sequences using AI and prompts and so on, which is an area I'm fascinated about, and I know Kris is too. But then we'll promise we will get Lee back on for episode 5, where we will address some of those questions that have been left unsaid. So, all that leaves me to do is to massive thank you to Kris and Lee, giving up summer holiday time to record this. I know people are absolutely loving this and enjoying it. Check out Kris's Substack, which will be linked to in the show notes. Lee's nothing to plug. He said hello. I think he said hello to your mum and dad last time. Lee needs to get some kind of brand, some kind of website here. Kris, final thing for you. Give us a little book update. What would you, if you had to put 100 quid on it, when could people get their hands on this book?
Well, if I do what I promised the publisher and get them some version of a draft manuscript in the next week or so, then hopefully we're going to shoot for April next year. Accidentally launched a tuition business in America 2 months ago, which consumed a lot more time than I expected.
Yeah,
so
that'll happen. Yeah.
So yeah, that did consume quite a bit of time. So but the bit where I need to dedicate my time to that is hopefully stepping back a bit. Actually, hoping Lee can take over a bit more of the things I was doing over the summer now, which gives me a lot more time to work on what's left of the draft manuscript, about 50% to go.
Perfect. So April, that's definitely 2026, right? Not 2029. We're hoping this book's coming out. Fingers
Definitely
crossed.
2026, yeah.
All right, you've heard it here first. All right, brilliant. Thanks so much, Kris. Thanks so much, Lee. And I look forward to speaking to you again soon. Bye for now.
Okay.
Thanks, Craig.
Bye. Thanks, Craig.
Bye.